Okay, so our next test is comparison test. So essentially you have two series because you're trying to compare them. We're going to call one A and we're going to call one B. Actually, let's not be so specific to even name this. You just got one, you got two. And you can tell this is a series because it's a summation of a sequence. So essentially this one's just telling you, and let's move this up a bit. This one's just telling you if you compare this, and let's say in one case A is bigger than B. Bigger than or equal to. If this one is, or let's say if this one is divergent, then we know this one is also divergent. So let's write that out. Let me make this summation smaller. Okay. And then if, let's say if the B series is divergent, then actually let's move this. Sorry, organization. Then the A series is also divergent. Now, the reason this is because if you have a series that is smaller than you and it's divergent, so let's just imagine this. So let's say this, we have two series like this. If this one doesn't converge to a number, then this one definitely can't, because this one is bigger than this one. So you would think that the smaller function would converge to a number. But if the smaller function doesn't even converge to a number, then this one definitely won't be converging to a number. So that's why if the smaller function b is divergent, then we know the bigger function a is also divergent. So just, if you get confused, just think about this graph in your head. You have a smaller one, you have a bigger one. The smaller one doesn't even converge, so the bigger one definitely can't converge. And then the other part of it is, let's say we had this A is is smaller than the B. Oh, actually we don't need these sums, actually. I'm just looking at the notes. Okay. Now, if A is smaller than B, and we're talking about the series of B again. Now, if B is convergent, then we know the A summation is convergent. I should make these all the same type of A. So now we think about this one. We have our graph, and we have some functions again. I'm just going to draw them like this. So now this time B is bigger. So that's B, this is A. So if this one converges, then this one has to converge, because this one's bigger than this one, and you'd think the bigger one wouldn't converge, and maybe the smaller one would converge. But if the bigger one converges, then it basically like squashes the smaller one too to make this one converge. Because remember, converging means the summation goes towards a number. So if the summation of bigger numbers, I suppose, goes and settles down to one number, then this smaller function also has to settle down to one number, because this one's essentially like pushing this one down to converge as well. So that's what the comparison test is. you just take two functions, two summations, you compare them to each other, and depending on their relationship and whether one converges or diverges, then you know the other is either convergent or divergent. And there's a very similar one called the limit comparison test. Oh, I'm out of room. Okay, I'm gonna move everything to one side and squish it a bit closer together. Okay, so hopefully that's still legible. And then we have the limit comparison. So it's very similar to the comparison test, except this time you're taking the limit of these two series. Or sequences? Sorry, I confused myself with that. So, in this case, these series have to be positive. They both only have positive terms. Or let's say have positive terms. Okay, so now essentially what this test says is if this approaches, you're going to put them on top of each other, and if it approaches some number c and this c is bigger than 0, then both converge or both diverge. Okay, so whichever one is, the other will be as well, as long as this limit approaches a number that is bigger than 0. So this one, let's do a practice problem. Okay, let's do a general one. So let me move this down so I've room. So I've got the summation of infinity, summation of n equal 1 as n approaches infinity, and it's 1 over a times n plus b, and then a is a positive number and b is a positive number. So we want to see whether this series converges or diverges. And the reason you do limit comparison compared to just comparison test is because you may have this type of relationship between your series, but instead of b diverging, it converges. And then you wouldn't know anything about a, because if the smaller one converges, we don't know. The bigger one can still diverge, because a smaller one converging can't force the bigger one to converge as well. Whereas if the smaller one diverges, then the bigger one is forced to diverge. So when you have a case like that and this doesn't work, then you can use limit comparison. So then you might ask, like, why do you even use comparison test at all when you can just use limit comparison for everything? And honestly, I don't know. Maybe a question would ask specifically for comparison test rather than limit comparison, but in my opinion, I like limit comparison a lot more because it encompasses all the issues that, or it does everything that comparison test does, and it encompasses all the issues that comparison test has. So it's like comparison test, but better. Anyways, limit comparison. Okay, so we have this series. Now what we want to do is we want to find a series that is similar to this one that we know the convergence or divergence of. Because then, remember, if one of them converges, then the other one converges as well. If one diverges, then the other one diverges. So if we can compare this to something that we already know the convergence divergence of, then we know the convergence divergence of this one as well. So to do that, what you want to do is take this at the very, like, its barest minimums, without any numbers, constants, just the variables. So if we see a and b are just numbers, so essentially at the bare minimum it's just 1 over n. So what we can do is we can compare this series with 1 over n. So we want to do a limit and we put this one in the numerator. So 1 over a times n plus b. And on the bottom, we have our second series, which is 1 over n. And we know that the series of 1 over n diverges. Because remember, this is our harmonic series, our harmonic p series. And that p, if it's greater than 1, then it converges, but if it's less than or equal to 1, then it diverges. So because this one is equal to 1 here, because this is like n to the first, we know it diverges. So now all we need from this limit is to get some number. So I'm going to rewrite this. Remember, if you divide by fraction, it's the same thing as multiplying by the reciprocal. So it's the same thing as a times n plus b times n, which I'm just going to write as n up here. And then the limit, if we take the limit as n approaches infinity, these both have degree 1, so we just take the ratio of the coefficients, which means this limit is equal to 1 over a. Because there's an invisible 1 here, and this a is the coefficient of that n. So this is definitely a number. So that means we know that they both have the same convergence or divergence. So the way we write that is this, the sum, or I mean the series, is divergent by limit comparison test with what we compared it to, which was the harmonic series. Oh, I just realized I wrote an equal sign there. That's supposed to be oh wait, no, that's fine. What am I doing? I thought that was a limit instead of a summation. Okay. So we know this one is divergent because this one is divergent. And when we compared them with a limit, we got a number. So that means they both have the same divergent convergence. So that's comparison test and limit comparison test. So I'll do the other ones in another video.